Consider the sequence a sub n where n is greater than or equal to 0, which starts 9, 21, 33, 45, and so on. First, because we are given n is greater than or equal to 0, it's important to recognize that the first term is a sub 0, and therefore a sub 0 is equal to 9. And now analyzing the sequence, notice how the terms are increasing by 12. 9 plus 12 is equal to 21. 21 plus 12 is 33. 33 plus 12 is 45. So because the terms are increasing by a constant amount, or we have a common difference, we should recognize this as an arithmetic sequence. To find the common difference using the formula, we have the common difference d equals a sub n minus a sub n minus 1, which means to find the common difference d, we can select any term except the first term and subtract the term before it. Notice 21 minus 9 is 12, 33 minus 21 is 12, 45 minus 33 is also 12. For part A, we're asked what is the next term in the sequence? Well, we know that the terms are increasing by 12, and therefore the next term is going to be the last term of 45 plus 12, which is equal to 57. Again, the next term in the sequence is the last term given of 45 plus the common difference of 12, which is equal to 57. For part B, we're asked to find a formula for the nth term of the sequence, which will be a closed formula for the arithmetic sequence. And since the first term is a sub 0, we use the closed formula a sub n equals a sub 0 plus d times n. If the first term was a sub 1, we would use a sub n equals a sub 1 plus d times the quantity n minus 1. So in this case, we're going to use the formula a sub n equals a sub 0 plus d times n, where in our case a sub 0 is 9 and d is 12, which gives us a sub n equals 9 plus 12n. For part C, we're asked to find the sum of the first 90 terms of the sequence, which would be the sum from k equals 0 to 89 of a sub k. Notice 0 through 89 does result in 90 terms. In this lesson, I will show how to determine the sum two ways, one by expanding the sum and another using the formula below. Let's do this on the next slide. So let's begin by expanding the sum. We have the sum s is equal to 9 plus 21 plus 33 plus 45 plus a whole bunch more terms. The last two terms are a sub 88 and a sub 89, which I've already found on the right. So at the end we have plus 1065 plus 1077. And now we're going to write the sum again, but reverse the order of the terms. So we have s equals 1077 plus 1065 plus a whole bunch more terms. And then the last two terms are going to be plus 21 plus 9. And now from here, we're going to add the two equations together. S plus s is 2s. So we have 2s equals, on the right, we're going to get the same sum each time. Notice 9 plus 1077 is 1086, and so is 21 plus 1065. So here we have a bunch of sums that are equal to 1086. Notice even here on the end, 1065 plus 21, again, is 1086. So the question is, how many 1086s do we have? Well, we have 90 of them because we're summing 90 terms, a sub 0 through a sub 89, which means you can write the right side as just 90 times 1086. And now to find the sum of the first 90 terms, we solve for s by dividing both sides by 2, which gives us s is equal to 45 times 1086, which is 48,870. So this is the sum of the first 90 terms of the arithmetic series. But I also want to show how we can find this sum using the formula shown below. We have two partial sum formulas for arithmetic sequences or series, depending on whether the first term is a sub 0 or a sub 1. Our first term is a sub 0, and therefore we'll use the formula s equals n plus 1 divided by 2 times the quantity a sub 0 plus a sub n. Let's just show we get the same result. we have S equals, the last term is A sub 89, and therefore n is 89, n plus 1 is 90, giving us 90 divided by 2 times the quantity A sub 0 is 9, plus A sub n is A sub 89, which we know is 1077. And notice how we do get the same result. We have S equals 45 times 1086, which gives us the same result of 48,870. Our book doesn't show this formula, so we should determine the sum using the first technique shown. I hope you found this helpful.